check. Hello, Ashwin.
Hello, sir. Good evening.
Good evening. Just a second. Let me just set up a few things. So, Ashwin, did you have any doubts in some last week's or last week assignments?
Yes, sir. So in the last weeks itself, so there's this question 3, 4, 5, 6. All of them were based on the uh, same graph.
Question 3, 4, 5, 6 has different graph. G2.
Right. Yes.
Mm-hmm.
Right.
3, 4 has
So,
different graph.
uh, so in fact, my logic, the way I thought about this was they had asked for node 3. So I thought that like I went in iteration since the very first one, that is the node 1 is A
Mm-hmm.
and node 2 is B. So then I thought that the payoff when you adapt AB for node 2
Mm-hmm.
is the highest, since one cannot change, since one is a given, that is a hardwired adopter of it. So uh, I thought that it's like 5 plus 2 minus 1, so it should be 6. So AB is the best strategy for 2. Uh,
For
and then subsequently, AB is the best strategy for 3 as well.
okay, okay, just a second. This is week 8, right?
Yes, we could.
Okay. Actually, I didn't make week 8 questions, so I need to revisit this assignment. Just a second. Give me a second. And till that, like, just also let's wait for 5 more minutes and see if more people are joining. Anyways, I'm posting a message in discussions. audible? Okay, okay, just a second. Hello, Manjula.
Hello, sir.
Okay, now I'll discuss the doubts session has in week 8.
उससे बड़े तीदुल कर दो तीदुल आज आज
People are not joining these sessions. Ah, okay. Some new faces. Actually, today only I got to know. Just let me share my screen. I can use the email ID provided by NPTL. This thing to access Q&A and email everyone instead of those who have joined the discussion forum. So I think that's why Riaz might have got the email. See, new faces. Hi Rahul. Hi Riaz. I think you are joining for the first time, right? Okay, anyways, let's discuss. So there is a correction in week 8 assignment. Correction in the sense there was a mistake. This b should be equal to 1, and then only the correct answers would be b and ab. So we have informed the NPTEL team and they will not consider these two questions for evaluation. Okay, Ashwin, you had doubts in 5 and 6 also, right?
Yes, so in the third, the question 3, uh,
Question 3, what is the exact problem you are having?
I cannot understand why it should be A, because so what I thought was AB, since the payoff like A plus B minus C is 6,
Just a
whereas
second, just a second. Payoff a plus b minus c is 6, correct?
it's just the highest compared to just A, which will be 5.
Correct. It should be ab then, na?
Yes, that's what I marked it.
Okay. I will inform the Megha. She has designed the assignment. Let me ask her if the answers are correct. Uh, just a second. Okay. Till then, please stay on this call. Okay. Um, so till week 9 still has time for deadline. No, let me check. Yeah, there's still time. So till week 8, these two questions only have doubts. So I have asked her, and she'll check. So because you're right. It should be a plus b minus c.
Yes, and the same for the next one as
Next
well.
for the same for the next one. So it will be ab for both. Correct?
Yes, that's what I think.
Mm-hmm. Max of a comma b is for ab. Okay. Could be how do I adapt to results better? Okay, anyways, let's leave out these 3, 4, 5, 6. Any other doubts in this week? Questions? Manjula? Hello?
Sir, if possible, can you explain that 8th, 9th, 10th once again? That one.
Arey,
Yeah,
it's 8, 9, 10th is simple. See, first of all, this is the thing.
very difficult to understand.
Difficult?
Yes.
Okay, anyways,
It is
I'll explain it.
what
I'll explain it.
you can just tell from starting onwards. Simply, you can tell me now, so that I can able to remember.
Okay, so see, first of all, my iPad is connected, right?
Because you have on the previous session, it's recorded, right?
Yes, yes.
That is very low voice, and I'm not able to understand who that one.
What is that?
You just explained that SIR model something, right? In
Uh-huh.
previous session, that one suspected and infected and recovered and all those things, right? You explained, right?
Mm-hmm.
And that is very low voice. So
Low voice.
voice is very low. That in a recording, but if
Let me
it is in a live session, it is nice.
let me check. Let me check.
But it's okay.
No,
You
no.
just
If that's a problem, I can change. I can because I had to reduce the quality of that video because its videos are very large. This is only written as delta time. This thing is written as minus times.
But thing is, I'm not
Just a second. Just a second. Just a
aware of
second.
that
Just
one.
a second.
The differentiation, that one equations and all.
Just a
It's
second.
very
Let me listen. Let me listen. Sign basically. I will make it. The voice is bit low. Yeah. I will check. I'll check if it's possible to increase it. Thanks for pointing out. Okay, so I'll explain that anyways. Okay. So let me share my iPad screen.
Here, actually, the susceptible to infection and recovered and vaccinated, these are all the informations, right? In
Mm-hmm.
in a social network, it's happening, right?
Yes, yes. Is my iPad screen visible?
Yes, sir.
Okay.
If possible, that 5 and 6 also, that how they
Five,
are calculated, that region and
five and six, the answers are incorrect. For five
yeah,
and for
but
this B, it should be one.
actually, how the concept they are explained, right? That graph and the first region, second region, and
I'll explain that first. Let me explain this, okay?
yeah, that also bit confusing actually.
Okay. Is my screen visible? iPad screen visible or not? Hello?
Yes, yes, visible, sir, visible.
Why can't I see? Yeah, now it's visible. Okay, so let me draw the diagram first. S, I, then there's R, V, beta, alpha, Si, this is tau, alpha, Vi, this is omega, Sv, omega, Rv. Okay, so this basically shows sort of COVID plot, um, how COVID has evolved or whatever it is. Anyways, let's not go into the philosophy of this SIR model. Let's study the rate of infection. Sorry, let's study these. Let's find out these terms. Okay. So first term is dou s. Sorry, dou s by dou t. Okay. So see, s is getting input from this thing tau. Okay. So that will be plus r tau. Correct.
Actually, what it is, dou s by dou t means, can you say
Dou s
it's
by
a
dou
long?
t is the rate of change of people in s per, with respect to time. Okay. So people are getting added at this level here, then people are getting removed at this level, and people are getting removed at this level. So there will be these three things. That will be, this will be, tau will be in positive, alpha will be in negative, and this omega will be in negative. Okay. Whatever it is, omega or this phi psi. So that will be plus r tau, then it will be minus alpha si times si. Why si times si? Because these are, s and I are always used together, because infection generally leads to a lot of other stages. So this, since alpha already is given, it is, hello,
Ah, yes, now it is fine.
sorry, I dropped actually, internet issues. So see, since it is given alpha is for si, so we have to use these si terms both simultaneously. then minus times phi psi whatever it is, SV, and it will be times S not V, because generally it's a scenario like infection. This term, the infection term, it is represented because this change, this I affects, this I plays a role in changing the rate of infection as well as the susceptible. But this vaccination is not changing that rate of infection because it's ultimately reaching susceptibility. Okay, anyways, always remember whenever you are using S, it will always be used with I. When you are using V means when like these terms like this are used. And whenever terms like alpha are used, which are basically targeting you towards infection, okay, then always along with the V, I will be used like that. Okay, so that's how these all terms are found. It's not like there is no specific uh, rocket science behind it. So if you want to compute delta I by delta t, so see, uh, delta I has one incoming, one outgoing, two incoming. Okay, so alpha Si times Si, see, that will be positive. Sorry, yeah, yeah, alpha Si times. Okay, then plus alpha Vi times Vi will be positive, and then minus beta times I will be negative. Okay, Manjula, getting it?
Yes, somewhat.
It's very easy. Like it's not. See, whenever you are doing do I by do t, you always have to include I type of thing in term here. Not per se I type of thing, but you have to see whatever this thing is doing. Whatever incoming is here, whatever outgoing is here. Outgoings are represented as negative, while just a second, it's loading. While incoming edges are represented as positive. Okay. Getting it? Hello?
Yeah, yeah, it's okay, sir.
You're
But
not.
it's a difficult way that symbols and all making.
Don't
Let's
worry.
treat them
See,
all.
see, see,
One
see,
more psi
see,
S, right?
see, see,
Psi
see. Arey,
SV.
listen to me, listen to
What?
me, listen to me, listen to me. Okay. Uh, this is symbols. Don't get confused by symbols at all. Okay. See, I'm doing it again. I'm sharing my screen. Let me show it here. Let me show in my laptop screen. See this thing. You are able to see this eye here.
Yes, yes.
Okay, just a second. This eye you are able to see, na? See, when you want to
Yes.
compute do I by do t, so this alpha is incoming here, correct?
Okay. Alpha SI, that is
Then beta is going outside, correct?
okay.
Then Vi is incoming.
Actually, what it means alpha SI, that means
Alpha Si is the rate
symbol.
at which susceptible nodes are getting converted to infected nodes.
Okay.
Then this thing tau means the rate at which recovered nodes are getting converted to susceptible nodes. Okay,
Okay.
so I,
So recover nodes will be maybe suspectable.
yeah, they can be. Say if someone has recovered from COVID, but again goes in the vicinity of people who are infected, there are chances of getting him infected again. Correct?
Okay.
Okay. So listen to me clearly. Okay. One last time, listen to me. When you want to compute do s, this thing do s by do t. When you want to compute do s by do t, okay, then you
Hmm.
utilize this thing. So see, alpha times si. minus s into I, because this rate has both the terms at once. And always whenever I is used, that I is always included. Okay. Then the next term, see, this psi times sv, this times, this is, say, this is going away. Okay. So see, this times s, because I will always take s instead of taking the node to which it's going. The rate of infection depends on s here. Ultimately it's going there, but if I'm computing this for this s node, I will use s only. Then the third edge is coming from r. Okay. So that's why I'm using from wherever this is originating, I'm using that. So tau times r, that is in negative, correct? Sorry, that is in positive. Tau times r is sorry, no, yeah, tau times r is positive. See here, minus, this is going away, this is again going away, times v, sorry, that times s. Whenever you are computing dou I by dou t, okay, so dou I by dou t means minus beta times I, minus beta times I. Okay, the origin is this point. Okay, then the minus alpha times si, sorry, plus alpha times si plus alpha times vi, this vi and this si, correct?
So incoming means you are saying plus, and it's
Incomings are plus,
outgoing is yours.
outgoings are in negative. Okay, that is
Okay.
pretty obvious stuff. Like, rate of change ultimately means sorry, this is basically showing the gradient. So when something is going outside from s, this means this s is reducing, so its graph will fall something like this, something like this. And when you're computing, when s is increasing, so its graph will go something like this. So when recovered nodes are getting added to infected, sorry, susceptible, so the susceptible count will increase like this. Slope will be positive for that thing, so that is why it is in positive. While for alpha si and this psi v sv, it is negative, correct?
Okay.
Okay.
Yeah.
Okay, any other doubts? Manjula,
Is
any
it
other
5
doubts?
and 6 in that same module? 5 and 6?
5 and 6, there is a correction. I have asked them to make it.
No,
This,
no, just can you explain this region, how they are placing this region?
how they are placing. I discussed it, I discussed it here for this case. Same thing will be applied here. It's not confusing.
No, I also have a doubt.
Sorry?
So in 5 and 6, when B is 0,
No. That's I have emailed now. I have emailed. Please check. This b is equal. B should be equal to 1.
yeah, so it is a mistake, right?
Yes, yes.
Okay.
Manjula, please. I'm suggesting you read this thing. I'll share the page number. Just a second. Hold on. Let me share the page number. Read that because it's uh, page number 231 to page number 234 or whatever, like the decision based cascade models. Just see it once. It's very easy to understand from there. The graphs, because it is like a lot of things are explained in this region thing. If you can see on my screen, this page, there are like multiple region thing explained. So if you just read these things, these are very easy to understand. Okay.
Yeah, oh,
Okay, then we have the next thing we was planning to start is graph representation learning, which will be taught in this week 10. And I'm covering the basics of that, so that because this is difficult to understand. Till now, the concepts which we have used, which we have studied in all the lectures, they are very intuitive in the sense because they don't require any prerequisite. But this graph representation learning will require prerequisites from your end, and that is why we need to study that. Okay, just a second. Let me share my iPad screen. So from now onwards, from this week onwards, I suggest you guys please join their weekly sessions because uh, this is week the this including this we will have 4 sessions and one extra session before exam so that I will discuss the not important topics per se. I'll discuss important things are which will help you in for your exam, which is on 26th October, right? So let me check calendar. How many weeks do we have exactly? So today is yesterday. 22, 29, 6, 13, 20. Okay. So on 20th of October we will have an extra session where we will be discussing all the topics from start to end, a bit of them, and they are like we will just revise, refresh everything, and we will have important discussions like what things will be coming in, not exactly what things, like how the questions will be asked in exam. The questions will be quite similar to the assignments only, but anyways we will refresh it so that you guys don't have to study a lot of stuff. Just quick revision of all the formula and etc. Till now. Okay, so I will teach GRL, that is graph representation learning. It's quite an intuitive, not intuitive, sorry, but quite an interesting concept, and I would suggest you go through this book if you want to learn more. I'll share the link here. Am I audible, guys?
Yes, sir.
Cool, cool. Okay, so this is a book by William L. Hamilton from McGill University. It's quite an extensive, comprehensive Go book where they give everything of how the graphs are used in deep learning and how they are represented in deep learning, what tasks are followed, etc. etc. So if you just go to a random page, you will find a lot of similar things, yet they are confusing. So this cards index but these formula are quite confusing. So that is what this makes this whole concept of graph representation learning a bit interesting, because then the normal statistical measures cannot be directly applied. Okay, so I'll share the link here. I'll also upload the book on Drive. Okay, so you guys can download it from here. It's free. The, like this PDF, there's no copyright on studying from this PDF. Okay, so let me start with graph representation learning. So what is graph representation learning exactly? If I'm asking you, so Sushma, what is graph representation learning? Just give me 2-3 lines on that. Hello? Am I audible?
Yes, you are audible, but I'm just downloading the book.
Okay, okay. And no. I'm just asking you, what is graph representation learning? What do you understand by graph representation learning?
So I have not gone through that
No problem.
ninth.
What do you understand from this term, graph representation learning? What is learning? Learning part is you want to learn something. Representation means you want to learn the representation of something. Then graph means you're trying to learn the representation of graphs. So what is exactly GRL? That is means we are trying to learn the representation of graph. Okay,
Yeah.
and representation means currently what we are studying is what we study till now. These are the measures for a graph. But how to represent graphs in some mathematical space? represent it? You getting my point, right? So
It will have nodes and vertices and edges.
nodes, vertices, edges are there. But if I want to, if I ask you, you want to compare two graphs, like you do for say two images. There are two images you want to compare. So how do you compare two images? How do you say like this image is similar to this image?
Pixel by pixel.
Pixel by pixel, correct? So
And here every vertex have same degree.
yeah, you can say like you can compare by degree, you can compare by pixel. But what happens when there is a very huge image? So when there is an image of size say 100 cross 100, so you have 10,000 pixels to compare. That is not a problem. But currently there are like 4K pictures. This means they contains 4,000 cross 4,000 pixels. So that will be 16, 1, 2, 3, 4, 5, 6. That is whatever it is, ones, tens, hundreds, thousand, 10,000, lakh, 10 lakh, crore, 1.6 crore computations. That is very high. So if you start running for loop, nested for loop, that will be 1 crore
So we can
computations.
we can use and operation.
So what effect will it have? Like it ultimately you have to run this for these many times, correct?
Yeah.
So that is all. That is the issue. So similarly for graphs, so once you have like 100 nodes are there, you can compute node degree, okay, blah 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 measures are there, and you can compare. That's easy. But what happens is when you have a graph with say 1 billion nodes, then what will happen? Can you compare it using manual or say looping? Can you compare it like that? It's very difficult. Ultimately, it's on resources. If you have resources, you can, but we want to create some efficient methods to compute these things, anyways. So that's where the representation learning comes into picture. Representation learning. So representation means representing a graph slash, I'm writing it for image just for now. I'll then move to graph slowly. Representing a graph slash image slash whatever they are in vector form. Once we have vector form, there are like infinite number of measures to compare. There's cosine similarity, there's Manhattan distance, okay, there are Euclidean distance, everything is there. So once you compute a pixel, if even if I convert this 100 cross 100 image to pixel, that will be 10,000 10,000 size vector, correct? If I just flatten it. Manjula, hello.
Yeah, yes, sir.
So this is one problem because first of all the size of vector is very high, the dimensionality is very high. Second thing is it is not uniform. Problem with it being not uniform is that if I want to compare it and any other image of 100 cross 101 or say 100 cross 110, so even though images can be similar, but these 10 pixels, these 10 extra pixels, they will cause a lot of issues in comparing. Okay, so what we do is, for similarly for graphs, if you want to compare a graph with 100 nodes versus another graph with 112 nodes, you cannot compare by converting it to vector form, say a vector of degrees of each node, like that. It's very difficult to do stuff when the size is not uniform. So ultimately, these two issues means we have to create a vector that is uniform and that is low dimensional. So basically, a graph is high dimensional. You cannot just use blah 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 things and compute stuff using exact graph. Okay, so that is the first part of this chapter. computing low dimensional vectors, and since the vectors will be computed using a uniform method, they will be of uniform size. Okay, so currently whatever we have seen the approaches, they have this problem, these two problems. And now let's go into the depth of these things. See, exactly each and everything is written like that only. You guys only told the exact answers, how to compare, etc., etc. So it won't be difficult for you to learn. Okay. So I'm coming to graph. I'm leaving the image thing out because it's out of scope right now. So how to use graph features for representation learning. Okay, so see, I have a graph. Okay, I have to convert this whole graph into a vector of dimension d, correct? Then I have another graph. Nodes are different. The nodes, count of nodes, everything is different. Again, I have to convert this to a vector of dimension d. Okay, this is our task. This is our task to convert it to d-dimensional vector. Then we can apply whatever downstream task we want to apply. Downstream means application. Apply, use these vectors in some application. Downstream task. So you want to compare similarity. So similarity will be compared using cosine metric. If you want to check if one graph is parent of another graph, then you can use some scoring function such as attention mechanism, etc., etc. These things are beyond the scope of the syllabus. I'm just explaining how this GRL thing can be used. So till now, any doubts, guys? Sushma, Manjula.
Yeah, no, sir.
Great. Okay. So now let's go to the techniques. Let's go to the techniques. Okay. Okay. So first and basic technique is you can just take adjacency matrix. But adjacency matrix of graph will have different dimension. So what you can do is simply you can just uh, apply matrix factorization to convert it to some r d cross d, d by 2 cross d by 2, whatever it is, and for all the graphs, for whatever size the graphs have, and then you can apply these operations. Then you flatten it, then you flatten, then it will be converted to r cross d, then apply task. One thing is that, so basically you can represent a graph using adjacency matrix and apply matrix factorization to flatten and then apply whatever tasks you want to perform. But the issue with this thing is again the same thing. For 1 billion nodes, the matrix will be 1 billion cross 1 billion, whatever it is in trillions, quadrillions. I don't want to know because the number is so big. So storing this matrix is a problem. Storing is problem. Then matrix factorization is problem again. Applying matrix factorization is a problem because you cannot factorize this matrix into halves or whatever way you like, just like that. Because, and even if you can apply, then reducing this from 1 billion to say 100 nodes is very difficult. You will lose a lot of information. Lose info. Correct? Till now, any doubts?
No.
Great. matrix factorization faces these issues, and if you see, if you will go through the lectures in this week, they will tell you exactly the same thing. Matrix factorization, etc., etc. We face a lot of issues like that. Okay. Then so how do we exactly compute graph embeddings? How do we compute graph embeddings? It's not exactly like that. So let me explain in simple way. So now say you have a graph. You have some graph here. Okay. You pass this graph into some ML model. Okay, so I have this ML model. I'm not going into the detail of ML model right now because that will be just a second. Because that we will be discussing in later stages today only. So you take some ML model, you pass this graph here, and you get some d-dimensional vector. Okay. So thing is that graph is large. This d-dimensional vector may not represent exact info. So what we do is we use data. Okay, data from graph to learn robust features. And this is a very vague sentence, but anyways I'll explain it in a few seconds, in a few minutes. So it's not given exactly like that in what is the 10th chapter. Okay, anyways. Okay, so yeah. So now I have some graph. I want to learn say features using machine learning. So how do we do that? So one way is you create some adjacency matrix as we did earlier. Okay, and then you take an ML model. Okay, and that ML model should take adjacency matrix as input and give output to these feature vectors. Okay, but problem is again the same. The adjacency matrix of two graphs will not contain the same number of that will not be of same size. So what you can do is you can pad it from outside to just once you pad it, you can get to the same size, or you can truncate some of the nodes, and then you can just pass this adjacency matrix in ML model, and you can learn this three-dimensional vector. Okay, but again the issue is the adjacency matrix does not fully represent graph. It just shows what edges are connected where, but it does not show any relationship like what do edges mean or what do nodes exactly mean. Correct? So we have not taken node features into consideration. Node features means say we have a graph of politicians. So there's politician A, politician B, politician C, D, E. A, D, these edge basically shows the say how these politicians are connected in on social media. Okay, who is following whom, etc., etc. But their individual identities are also present. So their individual identities are what party do they belong to, what party, okay, what state, etc, etc. Okay, so these features basically give rise to node features. These things basically give rise to node features. And if you accumulate node features, okay, if you accumulate, say I'm representing node features as an NF, if you somehow accumulate node features plus edge features plus adjacency matrix, then you will get some representation of graph. Correct? Am I clear, guys? Manjula, Sushma, hello.
Yes.
So vector in the sense it is having a magnitude and direction.
Correct.
No, adjacency matrix will have
Sorry.
magnitude.
Adjacency matrix basically does not is not a proper vector. It basically shows what edge is connected to what node. Okay. So adjacency matrix is basically, I would say, transformable. If you move one node from one place to another node, and if you keep a dictionary somewhere, so that will not affect the adjacency matrix. But if I move one coordinate of vector, one magnitude from one place to another place, so my whole direction of vector will change. Okay, so adjacency matrix basically is a scalar quantity that represents graph as a whole. If I move one node from one place to another, and if I'm writing what node it is on the top, then the adjacency matrix, it doesn't matter for adjacency matrix. But in vector case, all nodes should be represented. All the dimensions should be represented in the sequence the basis vectors are written. If I change it, then the order of that vector will be rotated or basically elongated. Whatever will happen, we don't know. Okay, so that is the case.
How this node and edge information adding to
And that
adjacency
is what I'm
matrix?
getting to, that is what I'm going to tell you. Okay,
Okay, okay.
I'm just telling you, if somehow we can merge this information. If somehow we can merge this information, then we can get this thing. Okay, so now how to do it? Okay, so I'm going step by step now. So first let's just use node info. Let's just use node info for graph learning. So you have, say, 4 nodes here, something like this: A, B, C, D. Okay, so how to learn, how to use node info? So you have some node info, say, in string form, correct? You have some node info in some string form, and what you do is, so say for node A, you have a string STRA, and then you use some of the string vectorization, text vectorization thing. Text vectorize, like say I use word2vec or but, then I will get a vector. I will get a vector that will represent this A. Okay, so that this vector will be, say, VA. Similarly, for all other vectors we will get, so for all other nodes we will get some vectors VB, VC, VD. Correct? Am I clear? Till now, any doubts? Sushma?
No, sir.
Okay.
Normally, word to vector means it will be converted into some number. It's called as vectors, right?
Yes. Word2vec, you search Google, you will find an interesting blog on Medium for word2vec. Just search Google, you will find this interesting blog. Just let me show you. Arey, exactly, I'm opening this PPT. Okay, so say this is count based methods like TF-IDF. I'm not going to do that. So there are other methods.
Can you share this PPT now?
I will share it. I'll share it. I'll also share this thing. So just a second. 40 no 821. So you can go through this page. This is our LLM series, large language model series, and you will find some interesting topics here as well. What to work, etc., etc. So you will, if you study this, you will get to know. The videos are also uploaded on YouTube for all the lectures. So till 13.1 or 2, the videos have been uploaded, and you can just look at these YouTube videos and get your concepts clear. Anyways, hmm. So once we get these node embeddings, now it's time to learn edge embeddings. Okay, so how do you learn edge embeddings? Any idea? Because adjacency matrix is just giving where the edge is. It's not giving what the edge means exactly. Okay, because ultimately the edges are getting connected because of some node features, and if node features are accurate in representing the node, then those edges should also be containing some of the edge features. Sorry, the node, some of the node information. So what we do is we take pair of nodes. So A is connected to B, A is connected to B, then B is connected to C, C is connected to D, and B is connected to D. And what we do is we take these nodes A, B, their node features, we pass them in some machine learning model or MLP, say multi-layer perceptron, and it gives me a score. So I will take some negative samples also, like A and D are not connected, then A and C are not connected. Okay, similarly, yeah, so once we pass A and B, the score should be 1, and if I pass A and D, the score should be 0, and I learn this relationship. So now once we learn this relationship, okay, then we utilize second last layer of this machine learning model as vector representation of this edge. So what I do is I just use this and this for a pair of nodes. What is an edge? Edge is a pair of nodes. So for a pair of nodes, I pass them, and this I get the second last layer as some d-dimensional representation of edge. So now we have node info and we have edge info. Okay, then we have adjacency matrix. Okay, so what we can do? So once you pass an edge, say node A and node B is equal to 1, node A, node D equal to 1, this adjacency matrix is there. You concatenate node A features, vector of A, plus node B features, vector of B, plus edge AB features. Okay, you pass this whole thing in this machine learning model and it will learn this relationship together. Okay, getting it? Any doubts? Any doubts, guys?
So we are assuming these edges are not weight. There is no weight on the edge.
No, not now. We are not assuming any weights right now. Okay.
Okay.
Okay. So, anyways, now I'm going to show you how This is a very basic thing. This is a very basic thing. You can just use it to learn the graph representation. Okay. Okay. So yeah, that is that. And I'm not learning the node representation using the graph information right now. I'm here learning the node representation currently using the text information. Okay, and this is very basic thing which you do for graph representation learning, and it is not used at all in research applications anywhere right now. So what we do exactly now? Okay, okay. So now let us look at how to learn node embeddings. Till now we have not learned node embeddings, we have just learned edge embeddings. And if you want to know more about this, then we have discussed in I think second last week, week 7 live session. We have discussed there. I don't know exactly. Please go through it. Yeah, week 7 only. Okay, that was on 10th of September. So if you go to the YouTube, you will find it. Okay, so how to learn node embeddings using graph. I'm not using any of the information and text using graph. I mean, ultimately I'll use the text information, but that information will be supplementary. But how do you learn node embeddings exactly? Any idea? Any idea, guys? Manjula, any idea how do you learn node embeddings using graph only? Not using text data, not using anything.
No, sir, no idea.
Sushma?
No.
Okay, so what do you have from a graph? Okay, what do you have from a graph? You have, say, so you have some node n. Okay, that node n, and then you have what is the objective? Objective is to get some embedding en. Okay, so what do we exactly need? We need to encode it from n to en. So we need an encoder that basically uses n to give output en. Correct? Encoder. Okay. Am I right? Till now, is there any confusion?
But, so embedding, that means you are saying about encoding the
Yes.
nodes.
Yes, I'm encoding it to some. This is d-dimensional. This is d-dimensional. Not, I should not write it like this. This belongs to d-dimensional. Okay, so this is d-dimensional, and now what we have to do is, so how do you basically in machine learning you train a model? You train a model. You use some loss function to train the model. Okay, so how do you train using some loss function? We have some embedding. How do we compare it? So there's a very basic step. That basic step tells you use a decoder. Okay, you use a decoder, and that decoder will again convert this en back to n, and then what you do is you use some of the metric. We have seen lot of measures, a lot of measures we have seen, a lot of measures we have seen till now. You use that measure to basically check if n fits that measure or not. Okay, but how do you measure like that? It's very difficult to just compute for n. So what you do is you basically use two nodes from the graph. Okay, like I said, I told you earlier. So for link prediction, for edge embedding, you use two nodes. So what you do, so you take node u, you take your node v. Okay, and what you do, you use encoder to convert it to EU and EV. Okay, then what you use decoder. You pass EU and EV here, and this passing this EU and EV to decoder should basically give you some similarity metric between U and V, some of the measures, some any measure. Okay,
Are you writing anything? Your notebook is not, it's stuck in your video and your notebook is.
it's visible. I can see it's moving. Sushma, is it moving? Uh, Hello, Sushma.
For me, it is new. I think some network issue.
Yeah, I think. Just wait a second. Wait a second. It will load. I'm
Yeah,
just wait a second.
I need to see that.
Okay, Manjula, wait a second. You will see. Okay. So this similarity can be any graph-based similarity. Graph-based similarity between U and V. Between U and V. So that can be Jacquard index. That can be what is the any similarity like common nodes, common edges, common neighbors. Sorry, common neighbors. Anything. So this basically decoder takes these two things and converts it to some sort of similarity, and ultimately what you get is what happened. Am I is my screen visible? Sushma, am I audible?
Yeah. But now I see is yeah, blank screen.
No, that's a blank page.
Okay.
Yes. So complete architecture is like this. You take you take two nodes from here. You pass them in encoder U, encoder V. You get EU, you get EV. Then you pass them to some decoder EU comma EV, which will compute some similarity measure. And this is learnable. This is learnable. I will show you how. Between U comma V. Okay. So this basically we are learning. This is learnable. This is learnable. This is learnable. And this similarity ultimately is learnable. So what similarity can be? So if you take say number of common nodes, number of common neighbors. So this node and this node has this and these common neighbors. So number of common neighbor will be 2. So if I pass 2, then it will be tweaked towards 2. So I'll show you how. Okay. So our loss function looks like this. We perform this operation on all pairs of U and V. All pairs mean doesn't matter if they have an edge between them or not. On all pairs of U and V. Okay. And the loss is again then that can be say decoder of EU comma EV comma similarity but value between U and V, and this is the predicted value, and this this is the actual value. Okay, and say this loss is mean square error loss. Mean square error loss represents basically y I minus yi hat square divided by number of n, this summation square root, like this. This is mean square error, mean square error, or you don't need to square root it. This is mean square error loss. Okay, so you compute. So say once you pass this thing, once you pass EU and EV, and you get output equals to 3.7, but actual output is 2, so it will be subtracted. The answer will be 1.7 whole square, that will be 2.89. So this is a very huge loss. So what model will try to do, model will try to converge it towards less loss. So ultimately till this value comes to 2, you will just keep on reducing it. And what you can do is you can use multiple decoders. Okay, you can use, say this is say encoder, this is encoder, this is decoder 1, this is decoder 2. You can use this one for common neighbors, you can use this one for Jacquard similarity, etc, etc. You can, then the loss will also change similarly. So S here is Jacquard similarity, S here is common neighbors, and you can tweak multiple decoders that will ultimately use the same encoder. And because ultimately for us encoder matters, we don't want to utilize decoders for later stages, we just need encoders. Okay, so once you use this, once we are once we train them, and once the loss is towards 0.000 or say 10 raised to power minus 9 or minus 8, whatever it is, then you use this encoder, because you know now the graph is represented accurately with respect to the measures we were computing. Okay, so then you use this encoder to basically pass a node n and getting an embedding en, and that embedding is again used with adjacency matrix whatever we want, and then it is passed and the model is, the graph mean graph embedding is obtained. Okay, anyways, this is very basic stuff. This is very basic stuff in terms of learning the graph. Okay, so if you go to page number 31 or 30 in that GRL book I shared, you will find this step as it is exactly. Okay, I'm not going into random walk embeddings, etc, etc, because that these things are very basic. Now let me teach you what is exactly graph neural network and how they are very similar to the measures which we have studied till now. So an important part of GRL is graph neural networks. Okay, and they are very good in representing graphs. I'll tell you how, I'll show you how. So Manjula, Sushma, can you tell me what do you mean by graph neural networks? If you have any idea, any basic idea of them.
Graph?
Neural networks.
No.
Graph
So we are going in a dip now. That one is called neural network. That means, so you have to check again and again until we get our destination, or until you get the accuracy. It's moving again and again, and we are find out in
sort of that only. Okay. So till now what we have done is we have used so basically here encoder, this encoder n, it basically takes say string text information, okay, to learn embedding. But what happens when we don't have that information? I cannot just simply use adjacency matrix, because using that I can use adjacency matrix, but this ML block here, which I'm talking about since a long time. Okay, how is this block learning? How is this block learning learning using adjacency matrix. That is what GNNs do. So this ML block is basically GNN, okay, graph neural network, and you will see it's very easy. So once let me show you. Okay, so say you want to learn the embedding of node C and you don't have any other information about them. So what you do is, can you tell me what are the neighbors of C?
B, D, and E.
B, D,
And E.
no, F. Sorry, E, sorry, E. Okay, so these are the neighbors of C. Okay, so what I can do is, I can create a row C. Okay, I can just take A, B, C, D, E, F, and I can just add one here, and one here, and I can just pass it some neural network, and that neural network will give me some embedding, some d-dimensional embedding. Okay, but this looks vague. This looks vague, but because how do we get this? How do we get this embedding? How do we optimize? How do we optimize, etc., etc.? This is very like very vague stuff. This neural network is very vague. This whole thing is very vague. Okay, so that is why we don't use exactly this neural network like that, and what we use is this tree. Okay, so now can you tell me what are the neighbors of B? Can you tell me what are the neighbors of B? A, E, C. What are the neighbors of D? C, F. What are the neighbors of E? C, F, B. Can you see very simple thing? Can you see what can you observe from this thing?
The repeated.
What is repeated?
So the parent and the leaf, the same.
C is repeated in all of them because it is ultimately a neighbor of all of them. Okay. Okay. So this is this. Just remember this thing because when so I discuss this, I'll tell you how. I'll tell you how. Okay. So in chapter 5 of this book, the GNNs are represented, and I'll tell you how they are represented. And okay, so we can compute embedding slash representation of C using its neighbors. Okay, so always remember GNN does two things. One is message passing, other is aggregation. Okay, so now remember this thing. I'll tell you how this basically represents message passing and aggregation. Okay, so ultimately just consider you have some initial embedding, text embedding, that is derived using, because text embeddings, problem with text embedding is they do not contain graph data, they do not contain graph info. Am I right? text embeddings do not contain graph info because they are uh, retrieved using some of the measures which have not seen the graph which we are using. So you can use text embeddings and convert it to graph embeddings. So what you do, you take text embedding of node, let me write it like this, text embedding of node B, which is the neighbor of C. Okay. Then you take text embedding of F, F or E, E and D. Okay, E and text embedding of D. And what you do is you aggregate them. So aggregate is basically, that is mean or sum, or most common measure to aggregate is basically mean only. So what you do, you add them and then divide by 3. Then whatever embedding you get, that embedding will represent text embedding of node C. Correct? Till now you got it? Hello?
Yes, sir.
Angela? Just don't get into the depth of it. Just try to understand how GNNs actually they were created. The purpose, the how they are basically utilized, the functionality of GNNs. Okay. So you got text embedding of C. But what happens is sometimes it's not necessary. It's not necessary that one hop neighbors exactly represent graph structure. So what you do is you take two hop neighbors as well. So to compute TEC, you need another TEC. See, no, I should not write it like this. To compute GEC, so basically this will be graph embedding of is node EC. So to compute GEC, you need TEC. Why? See here, scrolling, yeah. So you utilize TEB, TED, TEE, but here, if you want to compute, okay, look at this thing, So once I take two hop neighbors, if I take two hop neighbors, so what I'll do, I'll compute GEB, okay, GED and GEE using TE of these nodes, okay, correct? And now to compute GEC, I used GEB and GEE, not TE. I'm not using TEs of B, etc., etc., because these embeddings have been created by using the neighbor information. Okay, so they are basically graph embeddings. Okay, so that is how this whole graph machine learning is done. So what happens is if I do it for 3 hop neighbors and then 4 hop neighbors, you will start seeing this structure being repeated. So if I do here, then again I have to do B, then E, then D, and then again this thing. So ultimately what it is showing is if you go to neighbors of more than depth 2, more than depth 2, ultimately what you are doing is you are basically flattening out. Flattening out means if I use level 3 nodes, then GEC will be equal to GEB will be equal to GEE. These all embeddings will ultimately become equivalent because we are doing some aggregation again and again on the neighbors and neighbors and neighbors, and ultimately because since we are not using TE embeddings once we move further, so this means these embeddings will flatten out because we are aggregating and doing this stuff, So these embeddings will ultimately flatten out, and what you will have is you will have a uniform embedding that, sorry, constant embedding that is of no use. Okay, so that is why rule of thumb is nodes should be more than, so say you want to compute 3 to the power n, sorry, not 3 to the power n, 2 hop neighbors. Okay, the node should look like this. Node n, number of nodes should be more than some a to the power 3 like type of thing, and this is generally preferred as 2 2 point something, 2.5 or something. So 2 to the power 3 is basically 16, sorry, 8. So if you want to use, so this is basically how many times and how many hops. Okay, so if I do 2 to the power 3, this means I need at least 8 nodes to compute 3 hop neighbors, so that this repetition does not occur frequently. If it starts occurring frequently, then embeddings will flatten out and you will be left with this type of thing, sorry, this type of thing, which makes our whole thing useless. Okay, got it? Manjula, Sushma, got it?
I will have to go through your recordings later.
Yeah, I will upload it today only. Go through it. So
Okay.
that's why I'm just telling it. I'm just telling it. I'm not going into the equation part. I'm not going into any equation. I'm just giving you an intuitive feeling how these GNNs exactly work. Okay. So that is basically message passing and then aggregation. So message passing is basically neighbor, 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 and then aggregate the embedding of neighbors to get the neighborhood, the final embedding. So yeah, that is that, and I'm not going into attention part because that is beyond the scope of this thing right now. So what attention does is it does not give equal weightage while aggregating. So that is basically equal weightage is not given. So that basically gives us an option to allot dynamic weights to neighbors. There's a 0.8 times neighbor 1 plus 0.1 times neighbor 2 plus 0.05 times neighbor 3 plus 0.05 times neighbor 4. So this summation will give you the final embedding. Thus the whole thing is divided by 4 basically ultimately, but this summation will give you the final embedding. Okay. Got it till now?
Yes, sir.
Great. Attention, if you want to study, then I'll suggest you go through the link I have shared right now. Okay, so in this link, if you just go to 6.1, lecture 6.1, there's a video of attention. Okay, it's 5.3 and 6.1, they both have some of that sir explains attention network there. Okay, so yeah, that's that, and that's all about basics of GNNs. I'm not going into updation rules. I'm not going into gradient descent because that thing is beyond the scope right now. And so that's what I'm just telling you how to basically learn the features using graphs. So this ultimately what now important thing is just see this thing. Okay, when you use one hop neighbors, you use adjacency matrix, correct? Adjacency matrix A. Hello, Sushma.
Yes, we can hear.
Okay. When we use two hop neighbors, what do we exactly use? We use a square, correct? If you have studied, sir has taught in back in the lectures that if you square the matrix, this adjacency matrix, it becomes a two hop neighbor matrix. Okay, so this matrix will not, for C it will not contain B, C, D, but it will contain A, E, C, F, whatever the say, two hop neighbors are. Okay, for that it will be 1. Okay, so what GNN does is, so there are layers of GNNs. I'm not sure the screen is moving. Is the screen moving? Yeah, just a second, let it load. Yeah, so what GNN does is, if you just use one hop stuff, let me share my screen again. Is the screen visible?
Yes, yes, we can see.
Okay. So when you use one hop neighbors, it uses a matrix. Okay. And when we want to use two hop neighbors, so what we do is we apply another layer of GNN over this. Then this becomes two hop. So at step 1 we pass A, and at step 2 it gets automatically converted to A square, and then we have the final embedding whatever we want here. So GNN automatically computes this A square using message passing. What I'm writing. Yes. Automatically it computes using message passing, and this ultimately helps in aggregation. This A square, now you don't have to just hop two times or run, you don't have to hop two times. You can just go to the row and you can find two hop neighbors automatically, or you can use columns or whatever it is. Two hop neighbors, you can just find them automatically. Okay, so this gives you two hop neighbors, and then you aggregate and you get this embedding. So that's how you get node embeddings. Okay, then what you do is you use these node embeddings to learn link prediction, which we have studied in week 7. If you go to YouTube and see, then this basically gives you links, and then you learn link embeddings or whatever you want. Then what you do, you aggregate the same thing to get graph embedding. Okay, you use adjacency matrix of the graph, you use node embeddings, you use edge embeddings, you concatenate them, you pass to an MLP, you get graph embeddings. Simple as that. So we have still not studied this thing, how to exactly compute graph embeddings. So that we will study in next lecture, because by then you will have studied this stuff. You will have studied this mathematics of this stuff, GNNs. So once you get to know that, then we can start studying this. This whole thing which we studied today, that is very basic and an intuitive, uh, that gives an intuitive visual of how GNNs work. But once you go through the lectures, search lectures, then you will get to know the maths of GNNs. And once you get to know the maths of GNNs, then we can see how exactly we utilize adjacency matrix to compute graph embedding, to compare two graphs basically. You till now you cannot compare two graphs using the maths, using the intuitions which I have taught. You can only compare two nodes, you can only compare two links, you cannot compare two graphs. So once you go through this maths, then we will study. So next week please join, and from next week onwards we'll also just refresh some of the concepts of previous weeks, starting from week 1. That will be important for the NSEM exam, sorry, not NSEM, the NPTEL final exam. And I'll keep in mind the questions of the final exam, and in that manner I'll teach. So that will help a lot in revisiting. And any other doubts which you guys have?
Sir, I had asked one doubt about the week 7 quiz. Question number 1.
Question 1.
Week 7.
Okay. This is topological. Yeah, I saw this. What?
So I did not understand. So the alpha, even in the book it is given. So alpha is 1 when the source and if the surfer comes back to source.
Alpha. See, restart probability in supervised random walk, or say whatever it is. What that
Yeah,
algorithm
correct.
is. What that algorithm is. There's another algorithm which utilizes this probability. Page rank. Page rank.
Page rank, correct.
Yeah.
So if that random surfer he comes back to the source,
Mm-hmm.
then alpha is 1. And if he randomly serves other node, then alpha is less than 1. So in
Yes.
that case, alpha, it does not depend on topology actually. It depends on the
See,
random
see,
surfing.
you're confusing the language. It's
Okay.
what does alpha represent? What does alpha depend on? It's not written what does alpha depend on.
That is the restart probability, we say.
Yeah. So restart probability, what does it represent? So you have a graph. Let me actually no, wait a second. I'm shit. Okay, you know the question. I'm not sharing it on my screen. Let me
Yeah.
just show you. Let me just show you. So you have some alpha times some computation, then plus 1 minus alpha times some computation, correct?
Yeah. Q dash. Yeah. Q.
Yeah, I'm not writing it, I'm just telling you mathematic intuitively.
Yeah. Okay.
So say you have alpha probability of 0.8,
Yeah. Correct.
okay,
Yeah.
which basically tells if you do not find a node, if you do not find a link,
Okay.
okay, there is 80% chance you will jump to some restart node or random node in the graph,
Okay. Okay.
okay. So that is why that random node can ultimately be the next edge as well. Say if I remove this edge, if I remove this edge from here,
Okay.
if I remove this edge, you had this edge in the graph, if I remove it, then there's a
Okay.
80% chance you will jump to this node.
Okay.
Sorry, not in that manner. There's a 80% chance you jump to this node, and that node is already that node is already connected to this node. So they basically alpha. That's why alpha represents the topological information. Which node will you jump to? That depends on alpha. Okay,
Okay.
it's not. It depends. So optimization regularizer depends on alpha. What is the optimization rate? That depends on alpha, not
Okay.
the other way
Okay.
around. You had that doubt. I saw it. I saw it,
Yeah.
and
So
that's
I was thinking this alpha is like this 0.8 standard. It is calculated using some machine learning.
no. That is you can put whatever you want.
Okay.
Okay, it is also learnable. It is also learnable, but then you need lots of graphs, not in one graph. You need lots of graphs to learn it, and then you need to properly formalize some loss function, etc., etc. And that is very tedious tasks. That's why it is a hyperparameter, and that is manually tuned. So this your optimization ultimately depends on alpha. If you have some low alpha 0.1 times, so this means random jumps will be less, correct?
No more.
Yeah,
Alpha
sorry,
is
yeah,
less than
yeah,
1.
sorry, yeah,
Then it's more. Yeah.
yeah. So random jumps will be more. So ultimately,
More. So that means he doesn't get the surfer does not get the links.
yeah. So this optimization ultimately depends on the alpha, but alpha does not depend on optimization.
Okay.
Okay, alpha does not represent optimization. It represents topological information. Where you are going to jump, that is dependent on alpha.
Okay. Okay.
Okay,
Yeah. Thank you, sir.
okay. Just a second. Let me open that channel again. Discussion forum. Let me share my this screen. Okay, actually what happens is I always discuss these doubts here because in that channel now, in that discussion forum, there are only 30 people. Is my screen visible?
Yeah, I can see.
See, if I show you this thing, see, There are only 31 people, members. Let me check. Okay, 27 members are there. Okay, that's why I discuss doubts here in this session, which is online. So then you upload videos there. So that's why these doubts get discussed. Yeah, I remember asking. I remember you asking this question, and I discussed it in one of the weeks. I have discussed it as well. Yeah, you asked this, no? I have discussed it in one of the weeks. I don't remember exactly, but I've discussed it. So if you mentioned this on 12th of September, then on 15th of September I would have discussed it.
No, I have seen all your
So
recorded videos.
I think then I have
But
not.
anyway,
Yeah. Anyways,
thank
it's
you
now
for.
discussed. Okay.
Okay.
And then question seven, week seven, question 9 and 10, assignment seven, question 9 and 10. They will be these questions, these answers, these questions will be discarded. They will not be considered into final mapping because the answer is zero. Sorry, yeah, answer is zero. Actually, yeah. So they have changed the answer. Great.
Yeah, yeah. So yeah, it's re-evaluated.
Yeah, it's re-evaluated, right?
Yeah, correct.
Okay, so this means then this thing also in week 8 also the corrections they will do it. They will do it on their end because I emailed them. I emailed them a lot of times. Then only they changed it. So this thing they will also they'll check it. Okay, this thing they'll check it and they'll evaluate it. So don't worry about that. I'll ask them. Okay, once more. Let me just check whether I've got reply or not.
Sir, in week 8 now, you just see
Week 8. Yeah, week 8.
in the SIR model, a recovered node can be infected again. It's
Yeah.
true or false? But
Which one? Which
it
one?
is false, right?
Question one. Which question?
Second, recovered node can be infected again.
No, no, no. In SIR, it cannot be infected again because it's just goes sequential. So let me show you. Let me show you.
But we have seen SIR,
Yeah. If that this don't confuse that with this one. This graph is different. This is basically SEIR thing. Okay. SIR is a subset of that. Chapter is 7, right?
oh,
Let me check. Let me check. Let me show you. Is it chapter 7 or chapter 8?
right.
Chapter 7. Okay. So yeah, see, if you can see my graph, if you can see on the camera, this graph here, this shows susceptible, goes to infected, and that goes to recovered, and then it does not trace back. There is no feedback back to it. There is no feedback, so that is why the recovered node is not infected again or susceptible again. Okay.
Okay. But this one is different, right? That eighth question is
Yeah, that is
different.
different. That is different. That is this. This is not SIR model. This is say this is SEIR. This is a variant of SEIR. So SIR models is a variant of SEIR. SIS model is also a variant of SEIR, where the infected node again become infected, susceptible before recovery. Okay, so there's like
So
lot
that
of
means
variants.
here also that recovered node is going to the suspected.
Yeah, so
Seems like that.
yeah, this is variant. This is another variant of that model because it's not explicitly mentioned to you the another graph, any graph. So you have to consider the default setting. Default setting is the recovered node exits the graph, it does not become susceptible again. Okay, so if you check the equations of that equations, let me just cross check. If you check the equations, so then see ds by dt is negative times something. There is no plus term there, so this means nothing is getting added to it. Then recovered is getting plused, so whatever is getting recovered, it's not getting infected again, so there is nothing minus from it. Okay, then infection is plus minus because some of the nodes are getting recovered, those are getting subtracted, while just the nodes which are infected they are getting added, so susceptible which they are getting added. So that's why there is no feedback loop. So that's why this thing is not possible. The recovered node cannot be infected again, or it cannot become susceptible again. Both of the things. Okay.
Okay.
Okay. So any other doubts? Sushma, do you have any other doubts? I will check if the
No,
PPTs are
no, sir.
available. I need to ask sir. The thing is, I asked sir and he told me the PPTs are available on NPTL, so I didn't cross check, so I need to ask. Okay, and I'll share PPTs once I have them. I'll by the end of this week I'll share the PPTs. Weekly solutions are not possible because the assignments are made by a lot of people, and my the assignments which I have made, they are already uploaded, so that is not possible for now. Okay, week 6 question 4. What was the question? That this thing I also discussed. This thing I also discussed. Week 4. This thing I also discussed in some of the weeks. Yeah, most of the doubts are discussed only. So you guys have any other doubts? Sushma, you have any doubts?
No, sir.
Okay, so I seriously, I request you, please join week 9, 10, 11. What, this is week 9, right? 10, 11, 12. These 3 weeks are remaining, plus one bonus live session, because in those sessions I will be refreshing the basic concepts from start to end. Okay, so that will help you, because if you could not understand anything in lectures, I will just make it very simple, very clear, and that will help in understanding the clearing the understanding of the concepts, and ultimately the final exam, which is scheduled on 26th October. Okay. Virendra, do you have any doubts to discuss? Okay, so yeah, that's then. And one more thing was that. Okay, okay, Virendra, thank you. Okay, so next week we'll also discuss week 9, and week 10 should be live soon, because I have shared the assignment and I don't think so it's started now. Week 10 will be live by tonight, so you can start studying whatever stuff which I have taught today. That will be covered in week 10. Week 11 should. What is week 11? Let me check. Chapter 9 only, okay. So that is machine learning only, graph representation learning. Then week 12 is basically the applications of. So I don't need to teach you this stuff, because this is very basic, and this applied stuff, how the graphs and social media, they are used in real world, because some of the examples I've already covered in weekly sessions. So by week 11 or week 12 we will be just refreshing old concepts, and we will just do some of the examples from some of the some books. So there's network science book, I don't know exact, there's Albert Barabasi book as well, so we'll just do some of the examples from those books and try to understand the concepts. And what more we can do is we can also solve some of the assignment questions in those previous studied in those previous weeks. Okay, and if you want I can also go through this. Okay, what I can do is next week I can cover attention part here. Okay, and how attention is basically used in graphs and graph attention models, because this is this very basic thing, this is used in almost all of the deep learning machine learning stuff. So next week we'll study attention, we'll study these advanced attention mechanisms and how they are applied in graphs. These two things we will study, and then we will study the stuff. What stuff? For the final exam. Okay. So yeah, that's all, guys. Thanks a lot for joining. See you next week.
Thank you, sir.
Bye bye. Good night.